Our next guest and I spent our last 3 conversations over FaceTime trying to clean up other people's inline styles. He came all the way from Seattle to personally high-five some of you that he knows from last year. Very happy to have him here. Please welcome Brian Johnson. All right. You are over here, right?
Yes.
Is this you? Great.
This is me.
All right.
All right, and kind of like Sina, I'm not texting. I've got my notes on my phone. So so today I bring to you, this is a dark and morbid tale of string handling in Python 2. I know not the sexiest talk, but it is super interesting, at least I think. I told Shivani earlier that maybe the nerdiest thing I've said like in the last few months is that I could go on and on about string handling and string encoding. Like this could be like 2 talks or 3 talks worth, but anyway, give you an overview of sort of what the problem is. I was working at a small startup as an education technology company based here in New York. There were about 4 of us all together. And I was working on a project to build a web scraper in Python. I needed to download basically about 10,000 plus pages worth of data about Common Core problems and images and videos and things like that, so that we could curate them, add some metadata, and then serve those to parents of Common Core kids. I guess if you don't have kids, you probably have no idea what Common Core really means, but basically they changed the way that math is fundamentally taught in elementary school and middle school. Yeah, so this is what most parents think about it, and that's why my company was started, because like just imagine like your kid brings home some subtraction homework and subtraction looks nothing like how you expect it to look. And it freaks people out. So our idea is basically to gather all of the content out there on the web plus create more content in-house, and then we need to curate it so people can search for it, so we can put together like curriculums, all kinds of stuff. I'm going too in deep into that, but so the web scraping, that was my job. I decided to use Python. And then I had, so basically I made like a spider or like web spider, like a crawler, fetch all this stuff. I had another routine that added all of that metadata. And then it actually wrote it out to a file because it needed some hand curation by the business people, by the business and content people. So then read that file back in, index and Elasticsearch for real-time and natural language search, and then boom, there you go. So it's really not too complex. A little foreshadowing. Oh yeah, Common Core. I forgot I had this image on here. So you can't see this in the back, but that's like a standard KCC A1. So it says kindergarten counting and cardinality. A1 is like the series of what the kid's supposed to be learning. There's like different things we're supposed to do, count to tens and numbers to 100 that fall under this standard. There's different resources. This is from Khan Academy. KCC A2 is another thing. So basically like grabbing all of this, make it searchable, make it smart. So it was all going so well until when I looked in the database after all of my work, this is kind of what like all the text looked like. It was a soup of basically like question marks, random like wing-ding symbols, and I had no idea where I went wrong. So I went on a deep dive down like a deep dark hole of string encoding and string handling. And in order to tell you about how that ended up, had to, oh wait, where am I? I'm getting ahead of myself. All right, so anyway, I want to give you a high level kind of technical overview of the tools that I was using. So Python and Beautiful Soup. I had a list of website entry points. This is the Khan Academy one, Common Core maps. It's like a site map. So basically start there and then about a dozen other domains in order to find all the data. So fetch the initial page, scrape the page for links, capture relevant text and URIs for images, videos, and other media, categorize and scrape the pages that those links point to, write to a TSV, read to a TSV, store in the database. Storing in database kicks off a task to index and Elasticsearch. So high-level overview for the technical people. And if you've worked with, I guess, reading and writing some I/O stuff and all those kind of tasks, you might be able to point out a few places where I could go wrong in this. And I went wrong in each place. So I'll tell you a little bit about that. This is what I thought, and not how it ended up. So This discovery journey took me way, way back in time to 1963.
Can I just say you look great for your age?
Thank you, man.
Well, you took a time machine.
Everybody tells me that. So 1963, it was a simpler time in America. There wasn't really a lot going on. You know, folks were happy. The world was at peace. And so quick trivia question for you. Just feel free to call it out. How many natural spoken languages are there in the world? How many?
7,000.
7,000?
5,000.
Yeah, you'd be surprised to find out that in this much simpler time, there's only one language in the whole world, or at least in America. Kind of. According to the American Standard Code for Information Interchange, also known as ASCII. So this is the original standard. It was released, and you can't read this in the back at all, but June 17, 1963. So according to the folks and the Business Equipment Manufacturers Association, there's only one language we needed to worry about, and that was English. And this was the encoding that they came up with. In this simple time, you only needed 7 bits. Like a byte or a character was only 7 bits. It's amazing. So if you do your powers of 2, you realize that's 128 possible characters, but we only needed 95 because English is such a great and simple language. So you have 95 characters and numbers and then a whole bunch of control codes over here, 30 some odd control codes. So everything was like pretty great. And you might ask, like, what's up with 7 bits? Like, why would you ever do 7 bits when a byte is 8 bits? And the answer to that is that, like, computers, general purpose computers, are not the first digital machines. You can go way back into the 1800s with basically like Morse code and teletype. Morse code is like long, short, and a pause, but basically binary. And as soon as people started communicating, they needed a way to represent characters. And why would you use 8 bits to communicate a character when you could just use 7 or 6 or 5? And in fact, like teletype machines did use 5 bits for characters before. 7 bits gave them a little bit more room for things like control codes, like start transmission, end transmission, acknowledge, things like that. So kind of interesting. So we only needed 7 bits when we standardized around 8 bits to a byte. America's not greedy. We said, like, yeah, the world, you just use that 8th bit. That should be enough for you to encode your other languages, things like E's with accents, the entire language of Chinese, Japanese, all of that. You get the 8th bit. And after that, we have the birth of extended character sets and code pages. So for the Windows kids, you might remember dealing with code pages if you had friends from other countries and having to change the code page in order to properly render text that people were sending you from other parts of the world.
Yes.
Yeah. So if you're doing anything on the internet, like in the 90s, then you probably had to know about these code pages and when you needed to change it and how to guess what code page somebody else is using. And so if you aren't familiar with code pages, I copied something from Wikipedia that I can read for you. A code page, most well-known languages, excluding those for Chinese, Japanese, and Korean languages, and Vietnamese, all fit their code points, so all of their characters, into 8 bits and do not involve anything more than mapping each of these code points to a character, a single character. So that works pretty well for like most of the world. You take the English set and then you add 128 other ones and you can represent your language. So that was kind of cool, but switching between all these code pages was a lot of trouble. And once the internet came around, this stopped working as well. So a couple of engineers at Xerox and Apple decided to invent a universal set of character codes. This is in 1987, what we now call Unicode. All right, Unicode, my hero. Unicode to the rescue, right? So you might have inferred that I was working with data that was not Unicode encoded, and so when I tried to work with it, then everything went wrong, ended up with question marks and things like that. So, all right, so question for you guys. What is Unicode? Just like 1 word or 2 word answers. Anything? Or what?
Character encoding system.
All right. That's what I thought too. uh, I was surprised to find out Unicode is not an encoding. In fact, Unicode doesn't have anything to do with like characters. You can't really see all these things but that's I think like a copyright symbol, and that's a weird squiggly kind of thing. So Unicode doesn't have to do anything with. Oh, I got a mouse. These glyphs right here. What Unicode is this column here, which is a code. Like this one's 00A0, and then a description, non-breaking space. 00A8 is a diaeresis, or umlaut, I guess. So what Unicode is exclusively, it's a mapping, it's a dictionary. So it is a mapping from a code to what the character should be. So it's not text, it's actually, you could think of it as a number. These go from like 1 to basically 4 billion, and each number maps to an intended character. It's backwards compatible with ASCII. So ASCII started with bits like 00 through 111111, which is 127. So those codes are the same between Unicode and ASCII. Those numbers map to the same characters, which is pretty cool. So if you want to think about how to encode the lowercase a, that is an ASCII 6.1, that's in hexadecimal, or 97 in base 10. In Unicode, this is the common representation. U plus 0061, so it's the same. The only thing is you might notice is we took 2 more characters to do that. Like, do we really need those leading zeros? We probably don't. And this is where like encodings come in. So Unicode is a mapping of code points, these codes right here, to an intended character. But in order to actually transmit this, we need to turn into binary data. We need to serialize it, turn it into ones and zeros so that other people can work with it. And that's where we get UTF-8, UTF-16, UTF-32. These are all different ways of turning these code points into ones and zeros. So the basic case lowercase a, 0061, why don't we just lop off these 2 zeros and just do 61? That's 1 byte. We saved a byte. And if you're talking about loading web pages or transmitting massive data sets, getting rid of those extra zeros makes a huge difference. That's what UTF-8 does. You can represent characters using either 1, 2, 3, or 4 bytes. So it's a variable width encoding of Unicode. Whereas UTF-32 uses the full 4 bytes for every single character. If you're just using like English text, then it's taking up 4 times as much space, which is a big deal if you're talking about the web or even storage of massive amounts of data. So using this knowledge, you can come up with any number of different encodings to represent Unicode. You could come up with your own. There's actually only 136 defined characters right now, so you could probably come up with your own like more compact binary representation, and it'd be fully Unicode compatible. So I'll leave that as an exercise for you. That's some homework. All right. So quick recap, like what happened. Scraping pages, gathering all the data off of it, links to things like the text off the page itself, categorizing it, writing the TSV, reading that TSV, storing in database. And again, I was writing the TSV so that my coworkers could actually add some additional metadata, make some edits to it, change some language, stuff like that. Read the TSV, store the database, index, and Elasticsearch. So where did I go wrong? A lot of places. The first was a really poor assumption that there is a standard encoding for the web. There is no standard encoding for the web. If you've been around long enough, you know this. You've probably encountered a lot of like ISO 8859, also known as Latin 1 encoded web pages. So I was actually fetching a lot of ISO 8859-1, like Latin 1 pages, and I was trying to encode them in Unicode, ending up with all kinds of strange glyphs and characters. So that's number 1. Bad assumption. There is no standard encoding for the web. Also, I was writing these TSVs so that my coworkers could edit them. Excel uses whatever encoding is default on your system when the application was built. So it doesn't even provide you a handy way of changing the encoding, especially if people are using older machines and older versions of Excel. So that's a big deal. When I would write to TSV, other people would open it, Excel would save in a completely different encoding. I didn't know what it was. Python 2 represents all string literals as ASCII text. This is insane. That means Python's internal representation of strings can only handle A through Z, 0 through 9, underscores, dashes, no special characters. It's insane. You have to use a special Unicode string type in order to actually represent Unicode text. So that was a really bad assumption on my part too. I've been using JavaScript. Default encoding representation of strings is it Unicode? That's a good question. Anybody know? UTF-8? Okay. So that's why it hasn't really been an issue. I've been doing a lot of front-end work. So another lesson, Python standard library can be a trap. The types that Python standard library functions expect in return are inconsistent. You could give it a byte string, an ASCII string, and they could say cool. You could give it a Unicode string, it could say cool, and then slyly on the other side, it gives you back a byte string without like swallowing any errors. So Python standard library is a trap. Everything's a trap. So like the result is test everything and trust no one. If you didn't write the code and you're dealing with strings in Python 2, like you have to inspect it. Don't expect it to be a Unicode string. Like you don't know what it is. So you have to test it, figure out what the encoding is before you start working with it. Otherwise, at some point, something will break. Almost guaranteed. So what I should have done, there are a number of ways that I could have figured out the encodings of these pages I was scraping. One, which is super easy, is just to look at the response headers. Content type, a lot of times will tell you the encoding. I could have used that. I also could have looked at the HTML document. So there's a meta tag that will tell you the format of the text. So I just could have inspected that to find that this was UTF-8 or Latin 1 or whatever. When using desktop applications, be aware of default encoding settings. If you're working with non-developers, show them how to select UTF-8. Take their mouse and show them how to select it. If you're going to be reading that data back into some program that you're writing. And then you can also use an encoding detector like CareDet. A lot of data on the internet, there's no way to find out what it is by inspecting the data, whether the encoding is UTF-8, Latin 1, UTF-16, whatever. Sometimes there's a byte order mark, something like that. Not always. Some applications remove it. So there are some really great applications that basically use statistical analysis to tell you what it probably is with a great degree of certainty. So use an encoding detector. Like CareDet, that's a Python one. And then build a wall, sort of like a metaphor. So code that you write, always use Unicode strings. If you're getting data from someplace else, then test its encoding, turn it into Unicode or Unicode UTF-8. Somebody's going to yell at me after this for conflating Unicode and UTF-8 and like a mapping to the encoding, but whatever. So anyway, use Unicode in your application. Anything that comes from the outside, test it, convert it to Unicode, and then when you write out, convert it or encode it in UTF-8 to write to disk or to send over the network. So that wall, that's something that you're building manually, testing everything. And then transitioning to Unicode. And then finally, use Python 3. Python 2 is awesome. Almost everything has been converted from Python 2 to Python 3, so I don't want to hear any excuses. It makes so many of these problems go away. The default string encoding, or default string type is Unicode, and default string encoding, UTF-8 when you write out. It will save you a lot of trouble. Those traps in the standard library all go away. So that's basically my talk. And then I guess to leave you with one thought, which is I guess a little bit more philosophical, is that computer and hardware systems don't encode fundamental truths about the world in ones and zeros. Instead, they encode the most basic assumptions of the humans who designed them. So don't trust a computer because it's a computer. Test everything, trust no one. But I think that's probably like most important message I can leave with you. But that is my story of horror.
Cool.